Hey, everybody. So we're still talking about limits. We're still got a little bit of time talking about limits. So let's revisit what we said a limit was, remind ourselves some of our intuitions about it, and then add some new ideas. So the working definition we have for the limit of a function is what I've got written here. We say the limit as x goes to a of f of x is equal to L to mean the values of f of x can be made arbitrarily close to this number L by taking x close enough to a, okay? And in this, f of x is a function. It's defined near the number a, meaning near we mean on an open interval containing a. It may or may not be defined at a, right? That actually doesn't matter in terms of the limit. So let's break this apart just a little bit, give ourselves a little bit more intuition possibly, and then we'll do some examples and some new ideas. So let's look at a few pieces of this definition. So let's look at the part that says the values of f of x can be made arbitrarily close to L. So maybe let's say this in a more mathematical way. Arbitrarily close to L, here's a typical way to say that mathematically. We'll take a number that we traditionally use the symbol epsilon. It's a Greek letter, and epsilon is just some positive number, okay? Arbitrarily close to L means I can take any epsilon, any positive number, and typically think of it as a really small thing, right? That I can ensure that the difference between the function and the number L, okay, is less than epsilon. I don't know if f of x is above L or below L. I don't care. That's what the absolute value is there for, right? If f of x is below L, f of x minus L would be negative, but it's still close, right? I don't care if it's above or below. So this expression here, f of x minus L, the absolute value of that being less than epsilon, that's how we define arbitrary closeness. So epsilon can be any positive number, no matter how small. And if the difference between f of x minus L is less than that, that's a way of saying arbitrarily close, right? So this is an expression for closeness mathematically, right? What we're saying with this limit is that we can guarantee f of x minus L is less than, the absolute value is less than epsilon by taking x close enough to this number a. What do we mean by that? Well, similar idea. The difference between x and a, right? Again, I don't care if it's above or below. We're going to look in both directions, but the absolute value just tells us how far away, either a little bit below or a little bit above. Less than, this is another Greek letter, delta. Okay, so what we're saying is, given any small number epsilon, any tiny positive number, I can make f of x minus L, the absolute value of this, less than that number. I can make the distance of f to the limit less than that number, as long as I keep x close to a, and the closeness is defined by this little delta. This is a lowercase delta, all right? Let me make that a little less sloppy, right? So this is the lowercase of the triangle delta we've used before. So what this definition says, I'm not giving you the technical definition here, but that remember, go back to what I did last video, where the idea was that limits are like a challenge. How close can you make it? And you tell people how you can make it that close. The challenge is now epsilon. No matter how small someone makes epsilon, I can find a delta and say, well, as long as x minus a, the absolute value of x minus a, is smaller than this delta, then the difference between f of x and L will be less than this epsilon challenge that you gave me. So for instance, let's go over to this function here. This is a function we looked at earlier. F of x equals, I think I called it g before, so let's just stick with that. It doesn't really matter. G of x is a piecewise function. It's negative x plus 3 if x is less than -1. It's negative x minus 1 squared plus 2 if x is between -1 and 2. And then it's 3x minus 4 if x is greater than or equal to 2. So here's our piecewise function. Here's the graph of it over there. Let's look, for instance, let's examine this claim. I'm going to claim that the limit as x goes to, let's say -2 of g of x is going to be -1. So let's look at our graph to examine this. Let me put that point on the graph. -2, -1. There's our point. So let's zoom in on this point. What I'm saying when I make this claim is that if somebody else asks me, presents a challenge to me and says, so here's my point, -2, 1, and they say to me, I want you to ensure that the difference between the value of the, oops, let me fix that. Sorry, -2, whoops, come on, pen, there we go, -2, -1. That if I want to, so here's the y value is the value of the function, right? So somebody might pick a little interval, a tiny amount above and below -1, right? This distance is what we're calling epsilon, right? It's the same distance on either side. Well, I can pick then, if I notice, if I want to keep the values above within this interval, I just have to choose the x values within this interval, and this would be my little delta. And if somebody comes back and says, oh yeah, well, what if I make it a little bit closer? And so now they make a much smaller interval around the y values, I can come back and say, that's fine, I just need to pick a slightly different interval, a smaller interval. So for each challenging epsilon, I can come back with a delta, okay? So that's a little hint at the technical definition. It's not super important. Some people might like to see this a little more algebraically. If the pictures are starting to make some kind of sense, that is 100% where we would expect to be at this point. It takes a while. These are tough ideas. Let me clear this. So let's zoom back out, look at the whole picture. When we're talking about limits, so let's remember what our original intent was. We're really trying to solve this tangent line problem, right? And when we're trying to solve this tangent line, this tangent at a point, the difficulty was we were trying to look at a function that the point in which we were interested had a 0 in the denominator, okay? And so we're like, we can't compute the value of this function here. It's not defined there, and that's problematic. And so we came up with this idea of limits that look at what the function does everywhere but that point, and in particular, as it gets close to that point. We're looking at the behavior of a function as it gets close to some point, right? So in the case of this graph here, and the point we just did, we were looking at what did the function g do as x went to, as we brought x closer to -2, and the function starts heading towards the point, towards the value -1. In this case, it gets there, but it wasn't important that it got there. It was important that it stayed near that as it went, as the x values got closer and closer to it. In a similar way, if you look at this graph, we can say that the limit as x goes to, I believe this is -1, 2, as x goes to -1, didn't need those parentheses, of g of x is equal to -2, right? If you look at the graph from either side, it's heading right at that point, and it doesn't do anything surprising there, okay? One of the issues we talked about, however, was that sometimes we can't compute a limit. So in this particular graph, the limit as x goes to 2 of g of x, well, this does not exist, right? We notice that the function is defined there. We know that g of 2, if you look at the graph, this is the point, I don't know why it won't let me, there it is, 2, 2, 2. So g of 2 is equal to 2. But I can't put any interval around the x values that keeps the y values close to 2. Because if the challenge is made, let's zoom in here. If the challenge is made to keep the y values within this interval, no matter how small an x interval I come up with, I have a problem, because on the left-hand side, all of the y values are way below 2, well outside that interval that was challenged, right? And no matter how far I shrink it, right, I can get as close as you possibly want to this point, but any value below the input 2 yields an output close to 1, right? Very far from 2, almost a whole unit away. And so there's no interval where I can keep the values arbitrarily close to the number 2, right? So there it fails. However, limits can still tell us something about the behavior of the function there, right? This function still does something there. So the fact that the limit doesn't exist doesn't mean there's not something interesting to talk about here. And in fact, we can still talk about the function's behavior using limits. We just need to acknowledge that this function does two very different things depending on how we're approaching the number 2. For example, let's examine for x less than 2. So I'm looking to the left of this jump point in our graph. As x approaches 2, so that means I'm only caring about approaching in this direction, right? Traveling this way. So I'm putting in x values close to 2, but below it and getting closer to 2. We see the function does something very clear. It's decreasing and looks like it's approaching the point 2, 1, right? So for values less than 2, as x goes to 2, g of x goes to 1, right? We haven't really examined how we take limits yet. So we're using an intuitive approach here, using the graph and just seeing what happens, okay? We call this a one-sided limit, right? And we can write it this way. The limit as x goes to 2, and we put a little, so we're approaching from below, we're approaching from the left side, and usually we think of the left side of our horizontal graphs as the negative side. So we put this little negative sign there to mean we're approaching from the left. The limit as x approaches 2 from the left, or the limit as x approaches 2 from below of g of x is 1, okay? So in the same way we looked at those other graphs from both directions and determined what the limits were, in this case, we're just looking from one direction. And of course, we can do the same thing over here. If x is greater than 1, we can take than 2, we can take the limit as x approaches 2 from above g of x. And in this case, the limit is equal to 2 because we've got the point 2, 2, right? As we approach from above, right, we get a different value for the limit. And these are going to be our one-sided limits, right? And we use these little symbols, this little negative sign to be approaching from below and the positive side to be approaching from above. Everything else about the limit remains the same. We're still thinking of an interval. Instead of an interval around the value we're taking the limit at, we're taking an interval that ends at the value and looks at numbers on the other side. So for instance, this x approaching 2 from below means our interval is, here's 2. We're thinking of numbers below this value 2, right? Tiny little numbers in here getting closer and closer to 2. For the above side, we just look in the other direction, an interval containing 2 from above. And we call these two things one-sided limits, okay? Well, these are new, a little extension of the idea of limits, because they're still good at describing the behavior of functions, right? So we're using all this again to get at this tangent line problem. There are other places that limits come into play in math and science. And sometimes the behavior that you're interested in might be only from one side or the other. And in those cases, this one-sided limit is the piece of machinery you want, right? We looked at a function last time in a previous video. This was, let's call it f of x, x minus 3, absolute value of x minus 3 over x minus 3, right? This was equal to +1 above 3, -1 below 3, and this limit does not exist. However, we can take the limit as x approaches 3 from below, and that's going to be equal to -1, and the limit as x approaches 3 from above of f of x is going to be equal to 1, right? So we're just looking at the graph along, coming from the right from above. Our graph is approaching 1. In fact, it's there, it's already there, but it's still close to 1. Being 1 is very close to 1, so we can easily ensure that this function is close to the number 1 by simply taking any value above 3. Similar for -1 by taking values of x below 3. Now, there is a nice relationship between one-sided limits and limits in general, and we'll finish with this idea. Let f of x, let f of x be a function, defined near A. So near A, actually, I mean that very specifically to be on an open interval containing A. Oops, that's not how you spell containing. Containing, possibly not at A. So on an open interval containing A, we don't care whether or not it's defined at A. It just has to be defined at every other point in some open interval around A. And let L be a real number. Then the limit as x approaches A of f of x is equal to L if and only if the limit as x approaches A from below of f of x is equal to the limit as x approaches A from below of f of x, and both of those are equal to L. Okay, so let's go back to this other picture. Zoom out just a little bit, right? We took the limit here to be -1 as x approached -2, right? And if you look, the function is from both sides is approaching that number. And so the only way we have the limit there being -1 is if both the upper and lower limit, both the one-sided limits are approaching that same number, right? So it makes some intuitive sense. Versus a place right here at x equals 2, where approaching from the left and approaching from the right, we get two different values. This means that the function is going to different places there, and there is no limit for the reasons that we discussed before. And this works in both directions. If you know a function has a limit and it's at some point and that limit is L, then you know both one-sided limits have to be equal to L. On the other hand, if you know both one-sided limits are equal to L, then you know that it has the limit there and that limit is L. So an if and only if statement means you can take the causality in both directions. If A, if and only B means if you see A, you know B is true. And if you know B, then you know A must be true. So that's our connection between these one-sided limits and our general limits. This is a nice thing. There's a few implications here, right? First of all, notice that this implies if a function has a limit, both the left and right-hand limits must exist. And so sometimes it's easier to check limits from one direction or the other. And if you're interested to know if there's a limit overall, you might just check one direction and find out, well, it doesn't even exist from the left. I don't even have to check from the right because already we know the limit doesn't exist because it doesn't exist on one side, things like that. Okay, I think that's all I'll say about this. Thank you, everybody. I will see you next time.